In section 311 in our textbook called Speed of a Motor Load System, let's get into a little more detail on the specifics of the actual interactions of torque between the motor and the load that the motor is connected to. There's also, we're going to find out this particular component of speed. Now, working through this, remember what we took away from section 310, which was the only way that you can change the speed of a revolving body. Again, our revolving body is this electrical machine, is to apply a torque for a certain amount of time. We also found out in that section, that we could quantify the amount of time that we applied a certain torque to reach a certain speed, and we worked through that. So let's follow up on that and take this to another level in our understanding. Now we're going to be looking at three different figures. We'll be looking at figure 312, figure 313, and figure 314. And what we're going to see is something in common with each of these. We're looking again at three factors, and this is relating to electrical motors driving a mechanical load. And so we'll be looking at the torque developed by the motor, okay, and in this particular slide that's here. So the torque developed by the motor, the torque exerted by the load, and then there's another component that we'll be looking at here in terms of the speed, okay? So these are the three areas that we're going to look at under three different conditions. So he says in figure 312 that if we have a load and this load is coupled to a motor through this shaft, then the load exerts a constant torque, and it's going to act counterclockwise to the motor torque. And so if the motor torque, is, or I should say it's going to act opposite of the motor torque. In this particular case, the motor torque is shown to be clockwise, and the load torque opposes that. It's in the opposite direction. So what we can do, and we'll, of course, this is the one of the primary functions of this course, is by supplying additional current to this motor here, supplying, or increasing the level of current here, we can increase the torque that motor can exert. Okay, so this is our control here. And there's a whole very interesting portion where we'll get into this controlling this current that's supplied to the motor and all that. And that's the good stuff that we're working toward. So anyway, right now in this figure 312, we're saying that the load torque is equal to the motor torque. Therefore, there's no turning. There's no tendency to rotate, as Wilde says. So the only thing that might be occurring, and this would be at some atomic level, there might be some slight distortion of the shaft there that's connects the two, but that's invisible to us. But there's no actual turning that goes forth. So let's say that what we want to do is we want to cause this load to turn. So in other words, we need to make the motor torque greater than the load torque. All right, we need the net torque to be, excess clockwise, opposing the load torque. Okay, and there's a way to do that. And the way to do that is we increase the current to this motor. And when we do that, the motor torque exceeds the load torque. And while this motor torque exceeds the load torque, it will cause the load to rotate. And then once it reaches a certain speed that we want, we apply the torque for a certain amount of time. And then once we meet the speed that we want, we bring these two torques back to a situation to where they're equal to each other. And when we do that, the increase in speed will stop. It will neither increase or decrease. Now, that brings us to an important conclusion here revolving that. And then so here's the situation that we're talking about, right? You know, we increase the current, and you know, we applied a torque that exceeded the load torque. And so in this situation, we can bring it up to a certain speed. And then once that speed is acquired, we, you know, back off of the current and make the load torque and the motor torque equal to each other. And then it will maintain that speed. Now, at first, as Mildy says, it's difficult to accept because we tend to think when the two torques are equal that the motor should stop. But this is not the case. And you know, this is a fundamental concept that I want you to take away, is that when the torques are equal and opposite, then the speed is constant, regardless of what it is. And in effect, this motor load system is in a state of dynamic equilibrium. And we're running the load at a clockwise, you know, running the load clockwise at a certain speed. Now, let's take this to another different situation. And notice too, we'll be talking about this a lot in this course. Power is flowing from the motor to the load. All right, now let's go to the last figure here that talks about this. This is figure 314. And in this case, we're going to reduce the current such that we reduce the current so that now the torque of the motor becomes less than the torque of the load. Okay? And so what will happen now is the net torque on the shaft acts counterclockwise, and the speed that the load is rotating will decrease. And it will continue to decrease until this speed reaches zero. And if we continue where the load torque exceeds the motor beyond zero, it'll actually cause it to reverse direction. A big part of motor study is this idea of reversing motor direction. And we'll look at all sorts of practical aspects of that. And so, again, you know, once this, you know, as long as this exceeds this, you know, it's going to act in the opposite direction from zero and then starts to rotate in the opposite direction. So he concludes this. He says, in conclusion, the motor torque and the load torque are identical in their depiction in 312 and 313 and 314, but we're actually looking at three entirely different situations. And what we can also see here, and this is sort of the basis of, you know, hybrid vehicles and other things that we will look at, the load is actually inputting power to the motor in this case when its torque is less than that. But anyway, you know, the situations, you know, are the same. I mean, the situations are all different, even though we're looking at load torques, motor torques, and speed. The steady state speed depends upon whether the motor torque was greater or less for a certain period of time before the actual steady state conditions. And he says, whenever the motor torque and load torque are not exactly equal and opposite, the speed will change. The rate of change depends upon the inertia of the rotating parts, and we'll look more at that in some detail in some upcoming sections.